Now we will look at a couple of problems where we can use either the ratio test or the root test. For problem 1, we have the sum from n equals 0 to infinity of n squared over n factorial. For this problem, we will use the ratio test. This means we need to find a formula for a of n and a of n plus 1. The formula for a of n is straightforward enough. This is just n squared over n factorial. To find the formula for a of n plus 1, we replace our n with an n plus 1. And so we get n plus 1 squared over n plus 1 factorial. To find the limit as n goes to infinity of the absolute value of a of n plus 1 over a of n, we plug in our terms for a of n plus 1 and a of n. Thus we get this as limit as n goes to infinity of n plus 1 squared over n plus 1 factorial divided by n squared over n factorial. And we may rewrite this fraction as limit as n goes to infinity of n plus 1 squared over n plus 1 factorial times n factorial over n squared. It now helps to combine the terms that are similar to each other in our fraction. So we get this as limit as n goes to infinity of n plus 1 squared over n squared times n factorial over n plus 1 factorial. And we can simplify this to be limit as n goes to infinity of n plus 1 over n quantity squared times n factorial divided by n factorial times n plus 1. Notice that n plus 1 factorial is just equal to n factorial times n plus 1. This is because n plus 1 factorial is the product of the first n plus 1 positive integers, and n factorial is the product of the first n positive integers. And so we notice that the second term inside the limit simplifies to a 1 over n plus 1. Now if we look at the limit as n goes to infinity, we notice that the n plus 1 over n squared term approaches 1, and the 1 over n plus 1 is going to approach 0. And so thus we get that this limit is equal to 1 times 0, 0. And since this limit as n goes to infinity of a of n plus 1 over a of n is equal to 0, which is less than 1, we know that the series converges by the ratio test. For the second problem, we have the sum from n equals 0 to infinity of 2 to the n over n cubed. Once again, we will use the ratio test. This requires us to find formulas for a of n and a of n plus 1. Finding the a of n is straightforward once again. This is just 2 to the n over n cubed. And to find a of n plus 1, we replace the n with n plus 1 to get 2 to the n plus 1 over n plus 1 cubed. To evaluate the limit as n goes to infinity of a of n plus 1 over a of n, we plug in our formulas for a of n plus 1 and a of n. We may simplify this in a similar way to the previous problem. And so we get this as limit as n goes to infinity of 2 to the n plus 1 over n plus 1 cubed times n cubed over 2 to the n. Combining terms that are similar inside this limit, we get this as limit as n goes to infinity of 2 to the n plus 1 over 2 to the n times n cubed over n plus 1 cubed. And simplifying further, we see this as 2 times n over n plus 1 cubed. And as we take the limit as n goes to infinity, we can see that this n over n plus 1 cubed approaches 1, and so thus our limit as n goes to infinity is equal to 2 times 1, which is simply 2. Since 2 is a number which is greater than 1, by the ratio test we can conclude that this series diverges. For problem 3, we have the series from n equals 0 to infinity of 1 minus 3n over 3 plus 4n, all of this to the nth power. For this problem, we will use the root test. Thus, we only need to find a formula for a of n. The formula for a of n should be straightforward enough. This is 1 minus 3n over 3 plus 4n, all of this to the nth power. To evaluate the limit as n goes to infinity of the absolute value of a of n, we plug in our term for a of n. This gives us limit as n goes to infinity of the nth root of the absolute value of 1 minus 3n over 3 plus 4n to the nth power. Notice that we are taking the nth root of something raised to the nth power. Thus, these cancel each other out to give us limit as n approaches infinity of 1 minus 3n over 3 plus 4n. When we evaluate this limit, we end up getting a 3 over 4. Since 3 over 4 is a number less than 1, we know that by the root test, this series converges.